In this session, we are going to see about virtual memory, which is a memory management technique. So what is a virtual memory? Virtual memory is a technique that allows execution of processes that are not completely in main memory. So we all know that when a process is in main memory, it will execute. So when the size of the main memory is not big enough to hold a process, then comes the concept of this virtual memory, which supports execution of process which are not completely in main memory. So this main memory involves separation of logical memory as perceived by users from physical memory. It is actually a memory management technique which is used by operating systems to give the appearance of a large continuous block of memory to applications, even if the size of the physical memory is limited. And it allows the system to compensate for physical memory shortages, enabling larger applications to run on systems with less RAM. So this is the concept of virtual memory. So this is your physical memory and this is your virtual memory. You need some mapping between this virtual memory and the physical memory, and this physical memory will in turn access the secondary memory. This one is a secondary memory. So physical memory size may be limited, but the size of the virtual memory may be large enough to hold the entire process when it is big enough than the size of the physical memory. So the major advantage of this virtual memory is that the programs that can be larger than the physical memory can be stored in virtual memory. Further, the virtual memory abstracts the main memory into an extremely large uniform array of storage. See, we can have a large uniform array of storage, separating this logical memory as viewed by the user from the physical memory. So we can separate this virtual memory from the physical memory. So this separation allows an extremely large virtual memory to be provided for programmers when only a small physical memory is available. So the virtual memory will make the task of programming much easier. Why? Because the programmer no longer needs to worry about the amount of physical memory. So the task of programming becomes easier. And the concern of memory storage limitation is also removed from the programmer's mind. The virtual memory also allows sharing of files easily to implement shared memory concepts, and it also provides an efficient mechanism for process creation. So you can see this as the virtual memory, this as the physical memory, and this as the secondary memory. So from virtual memory, you can access from the main memory, that is physical memory, as well as you can access secondary memory. Coming to virtual memory, a program would no longer be constrained by the amount of physical memory that is available. You need not worry about the size of the physical memory at all. So the users would be able to write programs for an extremely large virtual address space, simplifying the programming task. So since each user program could take less physical memory, more programs could be run at the same time with a corresponding increase in CPU utilization and throughput, but with no increase in response time or turnaround time. This is the advantage of your virtual memory. Virtual address space. So what is this virtual address space? It refers to the logical view of how a process is stored in memory. So it will contain a set of virtual memory address that it can use. And this address space is private for each process and it cannot be accessed by other process unless otherwise it is shared. So this virtual address does not represent the actual physical location in the main memory. Virtual address is different, physical address is different. So how the mapping between virtual address and the physical address is done? The system maintains a page table for each process, and this page table is an internal data structure which is used to translate the virtual addresses into the corresponding physical address, which we will be seeing in the next slide. So your main memory will have set of physical address, and your virtual address will have set of logical address. Virtual memory will have set of logical address, and the user can't view the physical address directly. This logical address is used like a reference to access your physical address. So the logical addresses are generated by CPU, and the physical addresses are the addresses in the main memory. So you have virtual address, you have physical address. Translation from this virtual address to physical address should be done, and that is done with the help of a data structure called page table. And in the page table you have various page table entries. So virtual address will comprise of a virtual page number and an offset. These two together form a virtual address. Similarly, physical page number and offset, these two will comprise the physical address. So virtual address has to be mapped to physical address, and that is done with the help of a page table. So normally the page table will reside in the physical memory, and having to look up the memory pages directly in the physical memory will be costly. So that is the reason we are having a one more feature called TLB. TLB is translation look aside buffer. So this is a special data structure which will hold or which will store the recent page table entries that we have referred. And the memory management unit will work with this translation look aside buffer to map the virtual memory address to the physical memory address. So what is this translation look aside buffer? As I told, virtual address will comprise of virtual page number and page offset. Physical address will comprise of physical page number and physical offset, and this is the main memory. So supposing the virtual page number is this one and the offset is this one. So this will refer this page, virtual page number will check for its availability in the translation look aside buffer. This translation look aside buffer will have a tag and a physical page number. This tag is nothing but the virtual page number. So this 0x0004 is here. That serves as the tag. The virtual page number serves as the tag, and it has the actual physical page number also. So that physical page number will have an offset which is same as the offset of the virtual address. So this physical page number will be mapped here to the physical memory, location 4. So this is how from virtual address you can access the physical address which is there in the memory. So this is the role of a translation look aside buffer. So this TLB will act as a cache for the main memory unit that is used to reduce the time taken to access the physical memory. When you're storing the page table in the physical memory, and every time if you are accessing the main memory for page table, the time taken will be higher. So that is the reason we are going for a cache called TLB, which stores the recent page table entries. So this is also a part of memory management unit. It stores the recent memory translations of virtual to physical addresses, and it is a cache for page tables as well. Because it is part of MMU, the TLB it lives inside the CPU package, and that is the reason TLB is faster than the main memory, which is where the page table exists. Page table resides in the main memory, but this TLB lives inside the CPU package. That is why you can access this TLB faster. So accessing TLB is approximately 10 nanosecond, whereas the accessing of main memory is approximately 100 nanoseconds. So that is the reason we go for this TLB.